derivatives. So there's triple differentiation to get to W zeta from sea level. It's a challenge to do something like that if you got noise. Okay, this other one is a mission that really started all of this analysis 15 months ago. Is that somebody, an engineer at Jet Propulsion Laboratory, came up with a system that a new next generation scatterometer that measures surface winds, and then it measures the Doppler shift of the radar return, and from that infers the surface currents. And there's a host of questions about how well it can do that. They're convinced that it can do it pretty well. I'm willing to accept that their claim on that, at least at this point. Obviously, down the road, if you start to talk about $150 million for a mission like this, somebody needs to make sure it can do all that stuff. But let's just take their word for it that it can do it. And it measures the surface currents across a swath width of 1,300 kilometers with a 100-kilometer nadir gap. So it's about 10 times wider than the swath width of swath. And the nadir gap is about 5 times wider. Now, right now, the engineers are only willing to sign on to an accuracy of 0.5 meter per second with a 5-kilometer footprint. Now, nice thing about this is that to get relative vorticity, you only have to do a single derivative, and to get the W zeta, you do a double derivative. So it's one less derivative than is required for SWAT.
Like 0.5 meter a second is huge.
Yes, it is. Again, the whole point of the seminar. Okay. Now, if you actually look at the spectra of the noise, they're very different. So it's hard to predict actually what the outcome is going to be, how one is going to compare to the others. We actually ended up doing it empirically. So the spectrum from SWAT, because it's a derivative of the sea surface height, has this filter transfer function that turns out to be a sine squared. In a log plot, it doesn't look like a sine squared, but it's a sine squared shape here. And that's the filter transfer function of the centered difference. The difference is over two kilometer spacing. So it's kind of bluish. It wants to follow an f to the 2 line, but because it's finite differences, at the high end, it's a low-pass filter. So it starts out following f to the 2. The noise spectrum for this Wacom, as we call it, is white out to some point here, and then it rolls off from the smoothing of the raw data, which has scales of tens of meters or something. Turns out from the simulations that if we work with the baseline design of each of these systems, which is for 2.74 centimeter errors on SWAT and sea level measurements by SWAT, and 0.5 meter per second errors on this Wacom system, the Wacom resolution is very, very poor. It's off the charts poor. It's actually not even as good as what we can do right now from existing technology. So Wacom with a baseline design of 0.5 meter per second errors is not going to make it, not going to cut it for oceanographers. If we could get those engineers to drop that noise level down to a standard deviation of 0.15 meters per second, the simulations show that the resolution of the fields that we're interested in, relative vorticity and W zeta, is the same from Wacom as it is from SWAT. Now, this can be done if you throw enough money at it. But at an affordable level, by JPL, probably not. So we're probably not going to have that, at least not during my lifetime, but someday down in the future, possibly. So let's see what we can do with SWAT, and what we could do if we had Wacom with a 0.15 meter per second RMS error. So first, let's look at geostrophic speed and vorticity. So this is the same map that I showed you a few minutes ago. This is sea level, that's the geostrophic speed that goes with that, and that's the relative vorticity that goes with that. Terrible color bar over here, but I'm going to use the same color bar for all the figures that I show you in the next sequence here, where we're going to apply various smoothing to these fields with noise and see how much smoothing we have to apply to recover a good representation of what we see in the signal-only picture. So first, let's look at the noise with sea level. This is what that sea level map looks like if you add a 2.74 centimeter RMS measurement errors. It's purely white, uncorrelated noise. And you can see all the structures in here more or less. Maybe some of these little dits here are a little bit hard to convince yourself of there, but you can see semblances of those at least. And so you might think, like a lot of people think in the SWAT science team, that this is okay, we can kind of see what's going on. Let's see what that looks like when you add this noise and calculate the geostrophic velocity components from which you get the speed and the relative vorticity. looks like that. So, it's not such a good news picture here. Clearly we got to smooth this stuff some amount to be able to extract structures that look like these. And so what I'm going to show you is what happens if you successively apply more and more smoothing and see how far we have to smooth it until we get something sensible. So that's 10 kilometers smoothing. You know, already you're starting to see some stuff here along there in the surface current, but pretty junky over there for relative vorticity. That's 15 kilometers, 20, 25, 30, 35. Now by now, the speed's doing pretty well. You can see a lot of the features in the relative vorticity, but still not so great. Gotta keep jacking it up a little more. There's 50 kilometer smoothing, 60. That's looking pretty good. There's still a little bit of irregularity here, but you could put together the structure that exists in the noise-free fields with 60 kilometer smoothing. Now 70, 80, 90, and at 100 kilometers you can't tell the difference. All of these things look exactly the same. So let's try to summarize that in a simple plot. This is the signal-to-noise RMS ratio. And a signal-to-noise RMS ratio of 3.16 corresponds to a more traditional signal-to-noise variance ratio of 10. And I've just chosen that to be a threshold at which I say the measurements are good enough. That is, the signal-to-noise ratio is acceptably high. You might not want to do it that way. I tend to be pretty conservative about these things. You know, you might be willing to lower that to 2.5 or 2 or something like that. Choose whatever number you want. This methodology works exactly the same way. But let's just, for the sake of argument, use my number of variance ratio of 10. So what we want to do is to figure out the blue curves here are the signal-noise ratio, and this is for geostrophic speed, and this is for geostrophic relative vorticity. And where those curves cross the dashed line defines the resolution capability. Again, you might choose a dashed line that's down here, so you might get a little bit higher resolution than I would, because I'm conservative about these sorts of things. But whatever you choose, they're going to be comparable to what I've got here. And it says that you can measure the surface geostrophic velocity with a resolution of about 22 kilometers and the relative vorticity with a resolution of about 54 kilometers. Now, just to show you that I'm not just flapping my jaw about whack-em with a 0.15 meter per second noise, this is what you get for the signal-to-noise ratios from whack-em with that level of noise. And actually slightly better for the surface current estimates, better resolution, but not much. But it turns out, coincidentally, it's exactly the same, 54 kilometer resolution for relative vorticity. So in fact, these two systems are very comparable if you have a 0.15 meter per second measurement accuracy with whack-em. Okay, so this is what those three fields look like with no smoothing. This is what they look like with 60 kilometer filter cutoff, which is the next integer number I had above 54 kilometers. And that's a disappointment, right? You'd really like to see all this small scale structure in here. But as a reality check, and the good news, bad news, bad news, good news type thing, this is what relative vorticity looks like to us right now with the resolution capability of existing satellite data. So 60 kilometers doesn't sound very good, but there's a lot goes on between 200 kilometers and 60 kilometers. So while SWAT will not give much in what most people would think of as the sub-mesoscale regime, they will give us a lot of information. It will give us a lot of information at the short end of mesoscale and upper end of sub-mesoscale range. Now, to come back to Bob's concern about the validity of the Stern assumption that zeta over f is small, zeta over f is pretty small when you get to these kind of scales, 60 kilometers. It's definitely not when you get down to a scale of 10 kilometers. But at 60 kilometers, that's not a bad approximation. So I think that we're kind of lucky in that sense, is that there's some applicability of the Stern theory with the scales that we're capable of resolving. All right, so what I really wanted to do about this whole thing, what got this whole started, was we want to look at W zeta. So let's see what that looks like at sub-mesoscales. And here is that upwelling from the W zeta term. It looks, qualitatively very similar to what we saw from relative vorticity, but bear in mind that this is essentially yet another derivative of the relative vorticity. So it's not exactly the same, obviously. And the color bar here ranges plus or minus 30 meters a day, and it's super saturated in places. So as I said before, there's places in there where you can get close to 100 meters per day from this. But on those scales, the theory is not not legitimate. So let's see what happens, similar to what we did before. This is now 3 different choices of smoothing, 10, 20, 30 kilometers, and we're just looking at this W zeta term here. And these, the noise-free cases up here, this is what it looks like with noise, and you can't see anything out to 30 kilometers. Now there's 3 more, this is 40, 50, 60 kilometers. This is still pretty bad, it's kind of scratchy looking, but it's starting to look a little bit like what you see up there. Maybe not too bad, maybe that's even good enough for some people. And this is 70, 80, and 90 kilometer smoothing. Again, we can summarize all of that with a plot like we had before. This is what you get for SWAT, and it says that the WC term, that's the one that's from the surface current effects on the stress, the resolution is about 40 kilometers, and the resolution for the W zeta term that we're really interested in, the big one, is about 70 kilometers. And once again, just to show you that Wacom with 0.15 meter per second noise is very comparable. It gives 34 kilometer resolution for WC and 70 kilometers, again, 72 kilometers for W zeta. Okay, so once again, like we looked at before, let's see how things look. This is the unsmooth case here, and terrible color bar again, but I use the same color bar on all 3 of these just to put them on the same playing field. This is the pictures that you get for W zeta with 70 kilometer smoothing, and this is what it looks like from present capabilities. So once again, 70 kilometer smoothing is a disappointment. We really wish that we could get a better resolution, but a whole lot can be learned about W zeta on these scales that we can't see with the fuzzy glasses we have right now based on present existing technology. And I haven't really delved very much into this, but the picture I just showed you is this one here. These are the resolutions if you just look at instantaneous snapshots. The bottom picture, just to see how much things would change, is 30-day averages, and you can see that it's not quite halves the resolution, it doubles the resolution, I guess I should say. Doubles the resolution, halves the footprint size, or something like that. You know, so that's pretty good. Now we're getting down to 40 kilometers for 40 or 50 kilometers, depending on which system you're looking at, with 30-day averages.
Hey, Dali, what does the 30-day average mean if it's not a stationary field? Or is that an issue?
It means the same thing that 30-day average always means. When you get to scales like 70 kilometers or even 30 kilometers, they have more persistent than scales like 3 or 5 kilometers. And so those things evolve very quickly, but when you time average them, you know, upwelling here at this moment, and then the next day downwelling there, upwelling over here, those average out and they don't have much of a net effect. But some of the larger scale things evolve more slowly. So 30 days is just an arbitrarily chosen thing because I have 30 years of data and I want to see how much difference it can make. The right way to do this is to some sort of a thorough analysis, which is a daunting thought, considering how much analysis went into all of this. But to look at combinations of space-time smoothing and see if there's some sort of an optimal choice that one could use. Because it might be that you only need a weekly average and then you settle for 50 kilometer resolution or something like that. So I mean, the thing is, anybody who works with observational data understand that they can't resolve all scales of variability. If they could, then CTD profiles would give you everything you need to know about microstructure. But they can't. There's an averaging in a CTD profile that takes all the microstructure out, but there's still a lot left over that's of interest. And I think this, my point I'm trying to make with figures like this is the same is true here. We have to do an awful lot of averaging of SWAT data to get sensible maps of W zeta or relative vorticity that I showed a while ago. But still, there's a whole lot of structure in here. Think of this as microstructure that you can't see with the present technology over here. So space-time averaging is a very powerful technique, but obviously it doesn't allow us to look at every process. 30 years from now, maybe somebody will be able to figure out how to get this down to scales of 20 kilometers, and there's a lot more going to be learned. There's going to be approaching stuff like that. Okay, so the conclusions. This W zeta term is large on all scales. It's especially large when you get scales below 20 kilometers, which is kind of a threshold number maybe for sub-mesoscale. Maybe you want to call sub-mesoscale something like 40 kilometers or something. There's no clear transition from mesoscale to sub-mesoscale. And just mention that this term is implicit in all primitive equation models. It's not necessarily in a quasi-geostrophic model. It depends on how the model is forced. If it's forced by the wind stress curl, then this W zeta term is not there. If it's force